Dude, pumps suck. What? No, they don't. And if you pay attention to the rest of this video, you'll know why they don't. Now, most people think that pumps suck liquid, and that's actually false. They build pressure. And now you may be asking, well, how does a pump promote flow if it doesn't suck the liquid? Well, I'm glad you asked. Let's consider a balloon. After filling it with air or helium, if we were to let this end go, the gas would leave, right? Now, this isn't because the atmosphere is sucking the air out. It's because of a pressure difference. And the way fluids flow is from high pressure to low pressure. We force air into this balloon and cause it to stretch, but the balloon wants to return back to its original state. Therefore, the balloon is squeezing the air inside, increasing the pressure to be higher than the atmospheric air. That's why when we let the end go, the air goes from the balloon to the outside, from high to low. But we're not interested in balloons. We're interested in pumps, and more specifically, centrifugal pumps and how they work. But before we get into that, let's go over some terminology we need to know. There are two halves to a pump, the dry end and the wet end. The wet end is the side that sees our fluid, or as we call it in industry, the process. The dry end should never see process. Now the dry end consists of four major components: the motor, coupling, shaft, and bearing housing. The motor is usually an electric motor that spins at around 3600 RPMs, and some use variable frequency drives, or VFD, to adjust motor speed. The shaft is what translates rotational energy from the motor to the pump, more specifically the impeller. These are usually highly machined, needing to be extremely straight with correct chemical compatibility, and thus are high-dollar pump parts. The coupling actually goes in between the motor and the shaft, and this is usually flexible and helps account for minor deflections to allow proper torque transmission. The bearing housing is where the bearings for the shaft sit. There are usually two types of bearings for a pump: radial bearings and thrust bearings. Since the shaft in an overhung pump acts as a cantilever beam, we need a bearing to account for the radial deflections. Since there's a pressure differential acting on our impeller, there's a thrusting force along the axis of the shaft, which needs another bearing. Now, I mentioned an impeller, and you must be thinking, what on earth is an impeller? Well, good thing, because that leads us to now talk about our wet end. So this is a 3D printed model of the most common centrifugal pump, an OH1. Now let's see how our liquid moves through our pump. Process comes in from what's called the suction head. It is then fed into the eye of the impeller. The impeller is connected to the shaft, rotating at around 3600 RPM. The shaft does work on the fluid using Euler's turbo machine equation. Our process rides along the impeller vanes and enters the volute. This is where our pressure is built. The volute is this expanding spiral-shaped curve that leads our fluid to exit through the discharge head at a higher pressure. Alright, now I have a conceptual understanding, and it makes sense. Somewhat, right? But you're just taking my word for it. So let's look at the science and equations behind it. It's actually pretty simple, and we're going to be following Bernoulli's principle in the continuity equation. Continuity equation states that volumetric flow rate remains constant for incompressible flows. Q equals area 1 times velocity 1 equals area 2 times velocity 2 equals constant. So as the fluid is guided through the volute to the discharge, the cross-sectional area is increasing. Therefore, our velocity is decreasing. Now, when we look at our Bernoulli's equation, we have three types of energy: pressure energy, kinetic energy, and potential energy. Now, the fluid's change in height is much smaller than the change in velocity and pressure, so we can ignore that term. Now, our pressure 1 and velocity 1 are not changing in this scenario, so we'll equate that to a constant. Now, on the right side of our equation, as we can see, as velocity decreases, pressure increases. Now, a side note. Some pumps actually have suction pressure that is below atmospheric pressure. We know that our discharge is going to be higher than that, but that's not everything we need for our pump to work. If our pump's suction pressure is below the vapor pressure margin, we're going to start experiencing cavitation and flashing, which destroys expensive pump parts. The metric that is used to make sure that this doesn't happen is NPSH required, or net positive suction head required. Boom! That's how a pump works. Flow is pressure driven. And in order to get these higher pressures to promote our flow, our shaft does work on the fluid, which increases its velocity, and it's then guided through the volute, which is increasing in area. And from our continuity equation, we see that as area increases, our velocity decreases. And from Bernoulli's equation, we see that as velocity decreases, pressure increases, promoting flow. Oh, so pumps don't suck. Thank you for watching, and stay tuned for the next one.